Okay, so I'll get to abbreviate my pitch a little bit because Justin did such a great job. But I will focus on some of the things in a little more detail of what the station can provide and what, and then of course Ryan will follow up on how our customer service team helps you become successful in ISS. Mike, in the beginning of the week, started off with a great pitch to the team and explained how we've changed the culture of the office and the program to be oriented towards servicing our customers in the payloads area and how we've changed the paradigms. And I'll try to go through and show you in some of the facility and system changes that we've done how that works. But just before this morning, there was a questions to Dwayne, and he answered the question very nicely about how do you decide whether it's a CASIS or a NASA project, and the results and how the results are going to be used was a great answer. I wanted to show you a little bit more pragmatically on my side, because our job within the research office for NASA is to balance the resources across all our customers and integrate them and deconflict priority issues and try to help everyone be successful, because eventually the station does have limited resources, and we can only fly so many things, we can only draw so much blood, we can only take care of so many mice at a time. So in rough numbers, the way we divide up the resources is we have the Russian program and we have the U.S. program, and it's about a 50-50 split of all the resources available based on our different laboratories that provide services. Within the blue, the U.S. OS, we call that, our office, the Research Integration Office, allocates the resources, whether it's occupancy resources, crew time resources, power, up mass, down mass, along these general principles of this pie. 25% go to our partners, and the remaining 75% are NASA's. And between the NASA allocation, we have by law a mandate to divide it 50-50 between ourselves and our CASIS customer. So we work very hard on maintaining and providing fair amounts of resources to the folks that need them. We treat this as it's not at any one moment a balance. We treat it as a look ahead and look back over an 18-month period, and we try to maintain a trend. So if one partner is below in their allocation in one increment, and they have asked to fly a little bit less and make it up later because they want to focus their resources in a future period, we try to work that. We do that between ourselves and CASIS. And to date, Dwayne was perfectly correct this morning when he said we've managed to mitigate and keep everyone's priorities at the right where they need to be. And then I would tell you again, it's not NASA's job to sort priorities with any one partner's research. Our job is to fly everyone's highest priority and try to fit within these resource allocations. I won't spend much more time on that, but I will give you an example. Coming up on SpaceX 4, we're stepping up to flying rodents, and late in that development, we're going to fly literally 20 mice on that flight. Late in the development of that plan, CASIS developed a new customer and said, hey, we would like 10 of those mice to be for one of our new customers. And so we literally took a plan that was at first going to be just a demonstration flight and have divided literally the population of mice in half, and 10 are allocated for CASIS and their special customer needs, and the other 10 are for NASA. We're trying to, but as Marshall pointed out earlier, we're trying to make sure we get as much collaboration out of that research as possible, because there are literally only 20 mice in the end, and there are finite resources. So we do the best we can at trying to meet the expectations of all the customers. So Mike talked a lot on the first day about our change in philosophy, and our biggest change is that we really want to fly and operate payloads as soon as they're ready. We try not to scare people with templates and heavy requirements documentation. We try to make sure, we try to be as responsive as possible to bring the payload on board as quickly as soon as it's ready. We want to operate the lab like a laboratory, which will enable flexibility to our investigators. And Justin did a great job of explaining how we've increased our air-to-ground. We can actually have up to 3 or 4 air-to-ground simultaneously if we need them. We have the first 2 PACOMs been operating that way for about a year now, and it really helps the investigators communicate with the crew and getting across the proper results and understanding what's going on. We have significantly improved data rates now that are just starting to come online, and we've passed those data rates all the way down to the racks themselves and the payloads within the racks. And we also continue to try to make the integration process as simple as possible. We've done a number of things in trying to create software environments that just wrap your lab-based software. I think Mike talked about Stella, which is the primary tool we're using right now for the express racks. We've gone to the 110 power source, and we have expanded our remote operations. We're continuing to expand them. wherever we have our truck workstations to provide better, so that you can do your research wherever you live and want to live. We're trying to deploy a new test set, which means you can actually test your payload wherever you live in the world and not have to come to Marshall or Kennedy or JSC or any of the other test facilities we have. And we're putting up a delay tolerant network, which is basically it's a fire and forget kind of a system, which allows you to send commands or request data, and the system will take care of that, even though there's breakage in the links due to loss of signal or whatever. Design and verification is always an ongoing struggle, but we started a long time ago with the paradigm shift that our job is not your mission success. We really just need to make sure it's safe and that the payload plays nicely with all the other payloads on board. We don't interrupt each other. And so what we've done is we've exhaustively defined our interfaces, whether it's external interfaces or internal interfaces, that help you understand exactly how to go build your payload. We provide flight support equipment and hardware, as in for the lockers. We provide you actually the lockers for external equipment. We provide you the platforms that you need to build up off of in order to attach to our external sites. We've provided as much flexibility as possible, and we continue to try to push on flexibility for the design of the payload. We minimize our oversight. We don't ask you to come in and prove your design how it works. We just want to make sure that you're not going to hurt the vehicle or hurt someone in the space. And we try to also, NASA has a classification for payload or for any kind of hardware design, whereas Class A or Class 1 is the highest. We encourage Class D, which is a lower level of redundancy and allows crew intervention and in-situ maintenance on orbit in order to help you be faster at building your payloads and turning them around. And lastly, we've stratified as much as possible, and we continue to work on this, the verification and the requirements required to show us that your payload is in fact safe to fly. The key milestones in our processes are that we like to build our ICD with you as soon as you're ready, and we like to try to do that around a CDR whenever the payload decides that CDR is for their hardware. One of the more long lead items that we're still working at, trying to figure out how to get around, is the testing that some of the software has to do with the on-orbit integrated load, and that has to be at about 7 months prior to it being uploaded. That's still what we consider our longest pole in some cases, and so we're trying to create, and in fact we're actually looking at creating a standalone network on orbit where it just doesn't interface with the rest of the vehicle, which would allow you to basically fly your disk or your CD and not have to do the verification testing integrated with the facility at Sonny Carter. And then finally, you've got to train the crew. Sometime we need our products about a month before they go into training, but we actually have onboard training, so we can do that if it's simple enough. Pressurized milestone, we can manifest you up to months prior, but we also reserve spaces for standby payloads, and we've manifested payloads within weeks before the flight of the cargo mission. So if it's simple enough, we can get it up there pretty easy. And what really drives us on our cargo for packing is the packing, whether it's an HTV, a SpaceX, or we have one more ATV flight, which I didn't put on here, but ATV is also about a several month lead time. So we can, with the SpaceX, get down to several days prior to the mission. Externals are a little bit longer because HTVs need to build some flight support equipment, and so does SpaceX. They have to build some structure to hold the payloads. Even though we have standard interfaces, they still have to build these trunks. So they take a little more time, but nevertheless, it's still it's usually within the build time of an external payload, which takes 18 months to 2 years to build. So we're still working on that template. Justin talked a little bit about this, and I won't spend much time on this, but the way we do our business in the office is we meet with all the customers, and last year was the first time I included cases once a year, and project out 4 years, what do we need in the way of resources, and that's all resources. That's on-orbit to volume, up mass, crew time, return cargo, conditioned return cargo, external sites, and that allows us to, it's a strategic plan, but it allows us enough lead time to build up our inventory and make adjustments to the flight rates to meet those future customer needs, or to meet that projected market. So we meet every year, and we get together and say, what is your best estimate of what you're going to need over the next 3 years? And with that data, I can come back to the program and go, we need more of this and more of that. And you'll see in my pitch a number of things that we have implemented in the last 18 months even to meet these future needs. And I'll let Lorian go through the rest of it. But the important part I always want to point out on this chart is depending on the complexity of your payload, you can be entered into this process anywhere along this planning template. In fact, you can be entered even in the middle of an increment if you want to bring up additional equipment or whatever within a particular planning period. So we don't really hold, we have templates, but we don't really hold all our payloads to those templates. We try to accept them whenever we can in the process. So we have a number of facilities on orbit. I'm going to run through these very quickly. You can see these in all of our research manuals, but it'll give you a breadth of understanding of the types of things that are on orbit today, the things that Justin indicated that we can share and use with you, and which we are obligated to share with CASES customers. And we can also provide, we can help you with the international partner racks, because for every rack I'm going to show you, the partners have a similar rack that have different capabilities. And we can help work that relationship if you see a particular feature in a rack you need in their modules. Again, if you go to our reference guide, it's online and it's in the end of this pitch. There's a website. They can give you more detail on all these racks. But so I put the red boxes, kind of what Justin was pulling on the things that have changed. The general station provides the payload organization, 30 kW power average across all aspects of flight and all times of the year. We've been extremely, some would say somewhat limited in air to ground, but now with the new 300 megabits capability, we get a shared version of that. We have quite a bit of new downlink capability, and we're actually, within another year, have, I think, 24 kW of forward link, so we can actually start sending high-def TV up to the crew or whatever they need. We have 13 NASA racks for science right now on orbit. And we're actually, I put this note in here, looking at 4 more express racks to fly up, or 4 more versions of an express rack, anticipating, again, additional growth in our occupancy on orbit. We have a number of external sites. I think the numbers here are where the external sites are based on the different components, but NASA has actual rights to about, I think, 12 external sites, or 15, I'm sorry, 15 external sites. And we've seen such a demand for external sites, we're looking at hardware that actually allows to add 2 more to the addition of all those racks. So NASA has assets in other modules. I haven't broken them out here, but we have quite a bit of on-orbit capability. Another big resource issue that we have is, of course, crew time. This is a chart that shows you graphically how we've accumulated crew time. You can see over the first 9 to 10 years of the program, we only did about 500 hours, 5,000 hours worth of research. However, now, once we've reached assembly complete, the hill gets quite steep as we've focused on 35-hour increments, and we go to a 4th crew, we get even more time. So you can see the potential we have for doing research on ISS between now and 2020, just in this chart and the capacity. The other things I don't show in terms of resources are upmass. We have a little over 5 metric tons a year, starting in 15 for payloads and utilization, which is right now exceeds our customer demand, and so we have capacity available to get stuff on orbit. This is probably one of the key features of the U.S. side of this U.S. OS side of the space station, and that's its modularity. It's what's allowed us to maintain and keeps allowing us to maintain the space station for the next 20 years, or as required. We can change out entire systems at the rack level or even at the sub-rack levels, and so we'll go into that a little bit. So this is our workhorse, our express rack. We have 8 of these on orbit today, and it allows us to build lockers, put payloads in lockers, which are shown in the top left, which many of you should be familiar with, and outfit a rack on orbit. We can build them out on the ground and take them up and plug and play, literally. The environment that these racks see are based, I'm trying to show a microgravity environment here where you can see from this plot measured on orbit that the racks are basically seeing the microgravity environment that we predicted or was in the specification for space station. However, we have an isolation system on some of our racks that lets us bring that microgravity value extremely low and well below what the original design goal of the station was, which makes this, of course, a very attractive feature for many of our microgravity researchers. So I said we had 8 of these racks on orbit, and we're looking at expanding. NASA has 5 additional powered slots, one in the ISSS segment, one in the gym, and several more in the lab, and we're looking at building out those slots to provide for additional future customers. And this just shows the same express rack outfitted in different ways. We have on the right a mouse drawer system that had mice on orbit for 90 days. It was an Italian experiment, and it was a double locker. And on the left, we had a space drums, which is an acoustic levitation materials manufacturing system, and it actually consumes an entire rack. But we can change all of these out over time and replace them. Here's an example of a plant growth chamber that fits in one of our express racks called ABERS. And then, of course, we've talked a lot, I think many of you know about our NanoRacks customer. This is their creative solution of how to break one locker down into 16 smaller payloads. And they can gang these cube labs together into multiple combinations, and of which I believe we have 3 labs on orbit today and are looking at flying a 4th one. So we have quite a variety of packing sizes that we can accommodate on orbit. This is the workhorse of our cold stowage on orbit system. It's the ESA built minus 80-degree laboratory freezers. They built them on a barter for us, and we have 3 of these on orbit today, and are basically where many of our samples are stored. And then we have a whole cold storage fleet that we use for transportation and in backups to the Melfi on orbit. We have a Merlin that allows us to have refrigeration. We have a Glacier that goes down to minus 185 if we need to. And right now that's our primary SpaceX transportation unit. And then we have the cold bags to the right, which actually let us maintain minus 20 degrees on cargo being transported for up to 5 days. So we can get things back in a passive cold bag quite easily. Now, when we did the COOP this year, so this is one of the examples I wanted to bring up, we learned from the partners their increased demand for cold storage return and capability, and so what we did immediately was start to look at ways in which how can we improve the cold storage transportation system, because they were demonstrating to us that they needed more return capacity than we had today. So the way we've done that, or the way we've solved that problem, we believe we've solved that problem, is that the cold storage team has come up with a new freezer for us. It's basically taking the Glacier technology and improving on it and creating basically the same technology, but getting twice the capacity of samples in it for less volume. So what we can do is, instead of having one Glacier, we can have one Polar, and the Polar is half the size and can carry everything a Glacier can. So we'll get twice the capacity in return in conditioned or powered return. Also, with the cold bag, they've come up with a way to redesign the way the ice packs are manufactured, and we can almost double the return on our ice pack. So we'll have a minus 20 capability that is basically twice what we have today in return. So we're trying again to update our technology to meet the increasing resources of both CASIS and our other customers. And I'm running out of time. So we have a glove box on orbit. This is one of our workhorse glove box called the Material Science Glove Box. It provides 2 levels of containment, so payload only has to deal with 1 level of containment. And over the last 2 years, we've improved or added an upgrade which will make it compatible for all our life science experiments. We're also in the but once we saw the traffic going through this glove box, we realized over the last year that it's just not enough. That's one glove box. It's not enough for the amount of research we're looking at. So we're actually in the middle of a requirements definition phase for building another glove box, and we hope to have that on board within 2 years to help us split the load of this box into this facility into one other facility, and improve our planning and our crew time, our use of the on-orbit facility. We've also upgraded the video system, which will be deployed in the next few months on orbit, to a high-speed, high-resolution system that's all digital. Right now we have an older tape-style system. This will be all digital, and it'll be available for all the MSG and the future glove boxes that we build. So this is one of our more research-specific racks. It's a combustion integrated rack, and it has an insert, basically a small insert. Well, these inserts are tuned for different experiments, and based on whatever the particular investigator needs. In this particular one, they're studying the burning of fuels. So this is one of our core facilities that's available for customers. We have an MSRR rack, which is a materials science research rack, and in this one we study again with inserts, furnace inserts. We can study different materials that are going through mixing and solidification And here we have a fluids integrated rack. And again, I don't want to spend a lot of time because I'm already way past my, no? Okay. I got till 2, great. Human research, we have 2 racks in the ESA module right now that have human research equipment in it. We're looking at, and the HRF team is always improving the hardware that they have in these racks. They just recently installed new ultrasound and an eye studying equipment. And then we have a whole variety of exercise devices on orbit that are used for both countermeasures and for research. Justin talked a little bit about our Earth science capability as a platform. You know, it's taken a long time for NASA, even NASA, to identify the advantages of the particular altitude and inclination that we are at. But now that we've spent some time over the last 2 years working with SMD, they've learned the advantages or have identified advantages of using ISS as a platform for correlating experiments and using sensors that they have in the A-train and comparing with sensors that they put on the ISS. And so we have a number of payloads that are going up to provide a variety or additional data correlation points for payloads that they're putting on orbit. And then this just shows you that because of our unique altitude and inclination, that we get basically to cover the entire surface of the Earth within 3 days and can pass over the same point at multiple times during the day from the ISS, which is unique to the ISS altitude and inclination. One of the disadvantages of ISS is that it's not the most stable platform. We are a very big operational facility with disturbances from transportation. We basically fly this in the direction you see here on the page, but we have to flip it around with the stern into the wind every time something comes and docks, or we have to turn the boom into the wind when we do EVAs to minimize the charging of the station and the hazards to the crew. But we have characterized the various, what I call the wobbliness and the TIA, the torque equilibrium, attitude and what directions that we fly in, and we work quite closely early on in the process with our science investigators to ensure they understand these attitude changes and thermal environments that they're going to see in order to help them design their payload to be optimum on this platform. And that hasn't scared them away yet, so we're very encouraged by that. And this just talks about the microgravity. The wharf, the windows are one of the more unique options that we have in the space station, and the wharf rack was installed several years ago, which now allows us to put automated payloads in front of the window and operate them from the ground. So that's fully functional. We have iServe in the window today, which is basically a telescope with a camera on it and a pointing system that lets us select targets and document sites on the ground. The beauty of that system is that we can uplink every day new targets of opportunity. In this case, this was the oil spill out in the Gulf several years back. And then, of course, we have just whatever comes along in terms of natural phenomena and disasters. The cupola provides us a very unique environment. It's not so much for research as it is for situational awareness, but we have had several opportunities to use the cupola just because it gets you outside of the peripheral of the pressurized elements and gives you a more holistic view of what's going on around the station. Crews use it largely for robotics operation, which was its intended design, but we've also found the crews have found some creative uses for research, and we're seeing more proposals for using something like the cupola. This chart shows you where all the external platforms are located, and there's quite a few all around the station, and I won't go into the details of those, but they each have different viewing characteristics and very different power and data capabilities. And we'll talk a little bit. If you were here this morning, you heard about AMS. This was before it actually went up. I need to update my charts. But it's basically an SUV. We parked it on one of our more robust sites, the CAS site, a truss site, attachment site. And it's a huge anchor tenant of the space station. This was a smaller payload that we've just actually decommissioned off space station, and this is an earlier version of it. Actually, it was a materials exposure payload, and we actually brought the most recent version of this inside several weeks ago when the crew did an EVA, and it's beginning prepared to be returned. we're in the process of, we have an NRA out, and we're in the process of looking for a new sponsor for a new long-term future robotically compatible materials research platform so that we can go, continue to do external material sample experiments, exposures experiments. So this shows you our ELC. The ELCs are the backbone of the U.S.'s external capabilities in terms of putting payloads. We have 2 payload sites on each of the 4 ELCs. One of their biggest limitations is the data rate today. It's fairly low in terms of the rate in which we can send data back and forth between the payload and the space station air-to-ground system. However, we're in the middle of deploying a external wireless system. So technology is caught up and are helping us now to break that barrier. We're getting ready to deploy a 100 megabits shared system across the external, and all the external sites of the U.S. sites on the truss. And we're also looking at expanding it to the ESA and JAXA modules. And so this is the ESA module, and we're going to try to get coverage out to their sites. And then the JAXA module, and you can see the uniqueness of the JAXA payload sites themselves. They have both forward and aft viewing capabilities, nadir, and both zenith and nadir. So these are some of the more prime sites. NASA has access or rights to 5 of those sites, of which we're only using 1 at the time. And this shows you that, again, the capabilities. They have quite a bit of capability in terms of mass and data, and actually the only sites on the space station that have active thermal systems. So we can actually have coolant go into the payload. And again, we're trying to expand to 100 megabits in those areas too. So these are the upgrades that we already talked about, and we'll just keep pressing on. The other unique thing about ISS is, of course, the robotics arms. All of our external payloads are, from now on, have to be robotically compatible. We don't want to spend the crew time to do EVAs. This has presented some design challenges. However, we provide all the interfaces to the robotics arms, all the grapple fixtures, all the robotic SPITM type microconicals, the handrails if they're required for backup. And we also provide, of course, the other side of the interface, whether it's the PIU, which allows you to plug into that GEM site there, or the FRAM, which lets you plug onto one of our external ELC sites. And we conduct and we perform all the robotics analysis for you, and in fact do the verifications for most of that activity, because we realize that's a specialized activity. So this is an example of the SPITM. And these are some of the more creative solutions that have been coming up in more recent times about how to deploy satellites from the ISS. We're in the middle of building a thing called Cyclops, which builds allows us to deploy a satellite off of the GEM arm and out through the GEM airlock of a class and size that you see here. And I can't remember the weight and size, but you can see, okay, so it takes a payload up to 100 kilograms and a fairly large size satellite, and the size of a basketball or bigger. So it was a creative use, and in fact this is being built today by the JSC engineering team. The top one is the JSOD, which is the Japanese CubeSat launcher, and that's all actually have already been, and you've probably seen the videos of that. It's been in use. Below is in a concept by a company that's looking at maximizing the number of CubeSats that we can deploy by adding even more launchers in one site. So we would pack up to 50 in this one device, and then be able to send them all outside and then launch them every orbit or every couple of days over a longer period of time. So we minimize, again, the number of operations we do in the airlock and maximize the opportunity to use the station as a launching platform for these satellites. Unique features of the station, the near continuous air to ground. I didn't talk about it earlier, but one of the huge paradigm changes is that we have decided to, again, we've expanded the KU band, so it's fully redundant now, even though it's not a CRIP-1 system. We have a full up and a backup system for it, which is where most of the payload data and traffic flows. We've also, as I mentioned with AMS, broken into S-band, so we're now actually going to be able to put payload data on S-band if we really need it in the critical periods of time. The entire on-orbit payloads, or the data system is divided into different lands. Let's just be simple about it. And what we've actually started to do is blend the boundaries between those two systems. In fact, we have Robonaut operating on the crew land. We have more payloads moving to other networks on orbit. And we're getting a much more, I would say, barrier-free operations on orbit. So again, just an example of what we're trying to do to not have so much a segmented type of approach or operations. So we have control centers around the world, and if you have access to basically the internet, you can get your data just about anywhere in the world you need to, from a laptop in your hotel room. I'm not going to go through the vehicles because you showed us a great examples of the vehicles, but it's pretty impressive to see the number of SpaceX vehicles starting to come into the flow here. Our biggest constraint we identified in the COOP last year was return cargo, conditioned return cargo. And I've already explained how we're trying to improve that, but that's going to always be our biggest constraint, and we're looking for more and more ways to do on-orbit analysis in order to make the product that needs to come down is purely data and not so much the samples. So we're still trying to work with that. Research Guide series, a new thing this year. We have 3 here at the conference, and we have more coming out. I encourage you as these come out to use these, because these are where you get a more in-depth data of exactly how the hardware we have on orbit can support and how you can bring your research to ISS and in what ways. And then again, these are the various reference guides that we have that again describe the facilities in a lot more detail than I'm trying to do here today. And then I always like this chart because when I grew up, it was space was about black and white grainy TV and 3 guys that needed a shave. And station today is about a lot more than that. It's a variety of cultures, of races, social and economic backgrounds and disciplines. And it's in a huge facility with an amazing capability. And I'm inspired by it every day when I look at pictures like this. So, any questions? Yes, sir.
Have you guys entertained the possibility of attaching a large volume to the handrails on the exterior of the gym or some other?
We have a number of places on the space station that we could exploit. Handrails are a little tricky because they're designed for crew loads, EVA, and we've had payloads attached to handrails. But without getting into, I can get into the details of it, but we kind of try to shy away from it depending on the mass, because they aren't really designed for heavy loads and fracture criticality, and the way they're designed, they really were designed primarily as crew translation aids. But we have a number of places. In fact, Bigelow, we're working with the Bigelow Corporation. We have a SpaceX agreement to attach an inflatable module to one of our berthing ports. So we're actually using, a CBM port to put a module, and we don't consider that a permanent installation. So we have several places that we're looking at how do we exploit these unique areas that we're no longer using. Another one that comes up a lot is the top of the Z1 where the truss used to be for years as we went through the assembly phase. We have attached points there. Our biggest problem with new ports on the outside is getting data and power to them. And so that's always the trouble, because then we have to go out and run new cables and lines. So it really depends on the requirements, but we're open to many things. And we've found a lot of folks that press us every day to figure out new creative ways to modify the space station for them. So, yes, sir.
Ron, you mentioned on-orbit training, which I've never heard of before.
Yeah.
I'm aware of the intensive months-long ground-based training, especially for new hardware, especially for on-orbit lab-type work.
Right.
There's a lot of that hardware heading up the station soon. Could you give me some quick sense of what crew training would ideally be for that kind of operation?
It's already offered in a variety of ways today, because you're right, the crew's training starts years before they fly, and some of it is basics and fundamentals of just spacecraft design and survival. So we are trying to now set up, when we see the need to, for instance, we'll pick the one in front of us, rodents. We know the crews need a lot of specialized laboratory hands-on training on how to handle rodents and how to do dissections and how to operate in a lab. And so we are actually creating training courses today to get them the basic fundamentals of that. Now that's just basic skills training. So we're putting those kinds of things in place. Today we actually offer refresher training courses on orbit. So if the crew really wants to see it says, you know, I had that 2 years ago, I heard about that, I just can't remember. We can actually upload a video that some of our payloads have been making videos to talk the crew through what goes on. Sometimes the procedures themselves are already packaged to do onboard training, and the crew can just read through the procedure or read through the training exercise. So we actually have already implemented that. Another thing we've done as a part of the exploration support is we've actually done what we call, oh man, I can't remember the name of it, but it's basically where the crew goes and picks up a task and doesn't need air-to-ground interaction. A lot of our operations require air-to-ground interaction and checking off critical steps. Well, we've tried to go to a system in some areas and are experimenting with it to see if it doesn't create us a more flexible work environment where the crew can just go pick up a procedure and operate without having to communicate to the ground, and then at the end of the day they can just tell us, oh, I did all these things for you and we're done. To minimize, and in a lot of that we do that, we're trying that out for exploration because we are so proud of our air-to-ground and continuous coverage, but when you go for a Mars trip or whatever, you start developing lags and a lot of loss of signal periods, so you need a more of an autonomous training environment. So we're experimenting even in the real time how to do that. So it's an area that we're continuing to work. We actually had Dan Tani wanted to do a bunch of videos of how every day the crew could get up and put the tape in or the disc in of that particular payload, and the PI comes on and goes, hey, this is what you're doing and this is why it's important, and here's the steps you go through just as a refresher. So we're looking at all aspects, and it depends on the payload. Some are more conducive to that than others, and some you just literally have to specialize in, and we have to focus that crew member or that set of crew members on a task. So it's the key is flexibility, right? To be able to respond to all the different.
If I can just follow up on that for the onboard training, we recently had a payload of the space station that needed to repair in the facility, and within a month's time produce new procedures, new onboard training, and worked with video embedded in the procedure, and it worked beautifully. I mean, the crew is really smart.
Yeah.
And it's a beautiful dialogue, really.
And if the tools don't get in the way, they can actually do pretty good. Yeah, got it.
It worked very well.
No, I think that's, to me, the key to every aspect of what we're trying to do with this program is to find adaptive solutions that break the paradigm of how we used to always do it, which was train, practice, 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 and have a 100% successful mission, in a very short 7-day shuttle flight. This is more about research, learn as you go, what else do you need, how do we improve on the products, and how do we make the environment more responsive to the customers who are trying to get the data and try to understand. Okay, well, thank you. Oh, yeah.
One question.
One more.
Launching 50 CubeSats.
Yeah, not at once. It's not shocking.
Now, are these things that do ultimately
Yes.
burn up?
They eventually all have to. That's one of the key criteria is that they all have a ballistic coefficient that they will basically degrade in orbit within weeks to months. And then, so we track them once they're deployed. And something like that, the 50 launcher was, the idea is, again, is efficiency, crew time efficiency. Pack 50 of these, and then every orbit or every few days, send a few out, and let the PIs get their science and make sure you don't have confusion.
As long as they don't live up there.
No. Everything must have a ballistic coefficient that allows it to re-enter. I can't remember the number of months, but it has to. But we've deployed things as large tanks in order to get them off station and not have to bring them back. So. All right. Thank you very much. I need to get you out.